This lecture is over groundwater. So here's bell work from the previous lecture where we talked about streams. So pause the screen and then here are the 4 things that you need to write down. So I think this phrase is often misattributed to Mark Twain, but I really like it. It says, whiskey is for drinking and water is for fighting. I think this really describes how water is kind of thought about in the Western United States, as urban populations are growing and water managers are becoming increasingly concerned about water scarcity. And I think that's fitting for this talk because groundwater is one of our most precious resources and probably the one that's most imperiled. So we'll start with some basics about groundwater. First, let's talk about what groundwater is. When it comes to where fresh water resides, there's significant amounts of water that reside under the ground. And in Oklahoma in particular, that's our largest reservoir of drinking water and water for other uses as well. Groundwater is kind of misunderstood. It's a major component of the hydrologic cycle. A lot of people forget about that step, that water percolates into the soil and then moves or stays. It's a major source of water for a thirsty world. Most public drinking water supplies are in some way connected to groundwater. And I think that the reason that it's often misunderstood is that it's largely hidden from view, right? It's not like a lake where we can see when the water levels are decreasing. So groundwater is poorly understood by many people, and yet it's really one of our most precious resources. And it faces a lot of different perils today. It faces things like contamination, salt intrusion, exploitation, and other things that we'll talk about. So if we look at just the distribution of freshwater, you might remember from earlier this semester that about 97% of the water in the world is salt water, and that leaves us with about 2.53% freshwater. And of that 3% freshwater, if we were to break it down, 12% of that is the world's total freshwater made of groundwater. So out of all the freshwater that's available, this big chunk is groundwater. And that accounts for something like 0.5, 0.6 of the world's total water, which seems small, but consider that the only other viable source where we get things like drinking water from is rivers and streams, which are only 1% compared to the 12% of total fresh water. So groundwater is really one of our best resources for getting large amounts of fresh water. If we think about where groundwater comes from, obviously it's in the ground, but how does water get there? There's really 2 things that kind of lead to water infiltrating the ground. The first is simply that during precipitation, when it rains, there's some amount of water that infiltrates, and that word infiltrate means sink into the ground. So it moves through pores in the soil, and then it moves down to the water table. The really only other way that we get groundwater is that surface water, so bodies of waters like streams or lakes, infiltrate the soil around them, or they're connected to the water table and they feed groundwater. So there's really only 2 inputs that make groundwater what it is. In Oklahoma in particular, we have 23 major aquifers. So these are our large freshwater sources that are located under the ground. It says they store something like 320 million acre-feet of water, which is a lot. So in the picture over on the right top, all those different colored areas in Oklahoma, those are the different aquifers that exist. And out of all of them, the one that we most commonly think of here in Oklahoma is the Ogallala Aquifer, which is the largest aquifer. And out of that 320 million, it stores almost 100 million by itself. It says if you were to take all the water out of it, theoretically, just from what's in Oklahoma, and you put it over the rest of the state, it would cover the entire state in 2 feet of water. It's a huge resource that we rely on. In terms of what we use it for, about 80% in Oklahoma specifically of groundwater withdrawals are used for irrigation. So it's a major asset for agriculture, and lots of the states in the center of the United States rely on it for crop production. It says during peak irrigation day, so imagine it's the summer, it's dry, it's the growing season, and we're making crops, Texas County pumps just as much water as New York City, which is crazy to think about, right? Within Oklahoma, there's almost 10,000 groundwater permits. And if we look at the picture on the right, this is the reported amount of wells that exist in Oklahoma. There's over 100,000 wells that are pulling from these aquifers. And if you look at where they're concentrated, it kind of lines up where that previous picture was, right? Where all those aquifers are at. So when we're in class, I'm going to do this, but if you're at home, I encourage you, go to this link. We're just going to go through some of the maps on the Oklahoma Water Resource Board and look at the different maps about groundwater in Oklahoma. So what affects infiltration? If most of the water gets into the ground through infiltration, going through the soil, there are things that are going to infiltrate the amount that actually seeps into the ground and the amount that becomes runoff. One of the first ones is climate. You can imagine like temperate and tropical regions receive more precipitation, so there's going to be more potential for infiltration. So more rain events, more infiltration, think of it like that. Slope, this has to do with like the geology of the land, but steeper slope means the runoff is going to be faster, so less infiltration. So if we have a hill like this versus a hill like this, you can imagine water is really fast, going to move downhill. It doesn't have time to go into the soil, where here the water is going to be a little bit slower. Soil and rock type, we've kind of discussed this one before, but like pebbly soil can absorb more water more quickly than things like clay-rich soil. Vegetation, this one we mentioned back in the hydrologic cycle chapter, but remember that having more dense vegetation allows plants to absorb water and lessen runoff. Directly related to vegetation is land use. I mean, you can just imagine a paved versus a grassy area, which one is going to allow more precipitation to infiltrate. Obviously, things like impervious surfaces will decrease the amount of water that makes it to groundwater. And then the degree of saturation. That's just, has the soil been holding water before or not? Did it just rain yesterday? If it did and the soil is still wet, you can imagine it's not going to be able to hold a ton of water. So saturated land can't hold additional water, and that excess water is going to become runoff. If we think about, it simply being that things have to move through the soil to get to the groundwater, it's really not that simple. Not all of earthy materials and soils are equal in letting groundwater pass through. So like we were just saying a second ago, clay versus sand or grass versus concrete, there's obviously different materials that are more efficient at allowing groundwater to infiltrate. So if we have to think about what factors or why do certain soils behave that way, there's two things that we have to talk about with groundwater. The first question we're going to have to ask when we're talking about soils is how much space is available in the material itself, and that's something we call porosity. How much space is there in the pores of the soil, basically. The second one is how easily can water move through the material, and that's another thing called permeability. So we're going to talk about both of these things, but these two factors determine how well groundwater will move based on the material or soil that it's surrounded by. So let's start with porosity. Porosity is kind of simple. It means pores. So think of any open spaces that are left within sediment or rock. We often think of soil as being kind of like a really packed, tight, condensed thing, but there are soils that have open spaces with air and places for water to move. So whenever you have pores in between rocks or clay or pebbles, it allows precipitation to not only infiltrate and go further into the ground, but it can move in between those spaces. So even things like rocks, if the ground is made mostly of rocky materials, they aren't going to just completely condense next to each other. There's going to be fractures, cracks, or air bubbles that allow water to move through. Loose sediment is better at allowing water to move through. Even if we have tiny pebbles like sand, there are going to be spaces between them that water can still kind of shift through. And then, of course, just plain soil. Even soil has micro and macropores that we talked about this semester. So it varies depending on what we're talking about. You can see in the picture here from no pore space to a lot of pore space. But this is porosity. There are some materials that are going to be very porous, and you can see water has a lot of space in which it can move through and infiltrate, and other materials that are more non-porous, where they're more condensed and stuck together, and water has a harder time infiltrating. We can also just think of porosity as the percent of material's total volume made up of pore space. So it's actually something that we can quantify and measure. It's the measure of empty space between particles. So looking at the picture here, we can actually kind of calculate and measure these empty spaces that water is able to fill. So this is just an equation. I would suggest you know this is how we calculate porosity for a given sediment. It's pore volume, which is VP, divided by the total volume, VT, times 100 to give us a percentage. So again, the percent of this material, the percent of sand that is made up of pore space where water can move through. Even things that we think are impossible for water to move through might be deceiving. So if you were to see just plain bedrock, you might imagine that it's really hard for water to move through just these giant sheets of rock. But even things like slight fractures or tiny gaps between the rocks are actually enough for things to move through. Remember from earlier discussions about water this semester, we said water is a really good solvent and it's really good at dissolving things. A lot of precipitation is actually slightly acidic. And so when it rains, that water that first hits the top of the sediment can actually create tiny fractures. And over time, with a large enough amount of water, it can actually basically burrow its own way down. So this is an example of really big fractures in bedrock that are just formed from the natural acidity of water. So if porosity is basically the amount of pore space that we have for water to move through, what are some factors that affect porosity? There are two big things, the first being particle shape and the second being particle sorting. And we're going to talk about sorting first because I've got some images here for us to look at. But looking down here, when it comes to how the particles are kind of like aligned or spaced, we can call it either well sorted or poorly sorted. So well sorted means that the sediments that are making up the soil are all about equal in size. And because they're equal in size, they kind of sort or align with spaces naturally in between them. So very well sorted, they're all about the same size, and that means there's going to be more spaces here. So porosity is higher. More available space for water, higher porosity. Pore sorting is when you've got a variety of different shapes, and because you've got a variety of different shapes, smaller pieces are able to squeeze into what would be pore space. So if you look over at the picture on the right, now we have all these little tiny pebbles and things that are filling up the spaces where water would normally go. And if we were to like color it in, yeah, there's still some spaces here where water can move, but it's obviously not as much as the well sorted. So sediments kind of exist on this continuum between very well sorted and very poorly sorted, depending on the sizes of the materials or the particles within the ground. I said a second ago that shape matters. Rounded particles are the best for porosity, and that's because rounded particles tend to be well sorted, meaning if you put a bunch of circles together, you can imagine there's always going to be those gaps in between them, right? So if we look here at the pore space, rounded sediment allows for bigger pores, basically. So larger porosity. They also tend to be well sorted, like we said. Angular particles, on the other hand, like in this picture or this picture over here, they don't all match up evenly. And because they can't all just match up evenly, they leave tinier pore spaces. So this is an example of poorly sorted. You're going to have pieces sticking into the spaces where you normally would have pores, and therefore you've got less porosity. What is kind of interesting to me is that porosity doesn't depend on particle size. It doesn't matter how big or small these things, it matters the shape and how they're sorted. So that's kind of interesting because maybe you would think that like smaller particles would have less space. So like in the pictures down here, we've got several different sized pebbles, but if we were to actually zoom in and look at all the pore space in between them, they all have about the same porosity. So it doesn't matter how big or small the particles themselves are, it just matters overall the shape, and the shape kind of determines how they're going to sort. So that was porosity. The second thing that we need to consider is permeability. And we can kind of just define permeability as a material's ability to allow a liquid to pass through, or aka how well can water move through that material. And you've probably heard these words before, but a material can be either classified as permeable, meaning that water can move through pretty easily, or impermeable, which means that water may not move through at all. There are three big factors that are going to influence permeability. There is porosity, of course, the amount of pore space that is available in that particular sediment. If we look over here at the right, for instance, if we were to calculate porosity, clays only exist between 3 to 11%, whereas sands are 18 to 35%. So naturally, porosity controls a little bit of how well water is going to move through a space. Second one is size of pores. So obviously, larger pores means more permeable. One of the reasons that clay has low permeability is because it has tiny pores, and it takes longer for water to move through them. Pebbles are more permeable because they have larger pore spaces. And then the third one, interconnectedness of pores, just means like the degree to which those pores are connected. So pumice, for example, is a type of rock that has a lot of pore space, but they're not connected. So if you imagine we've got a lot of pores, but they're all kind of sealed off on their own, then you can imagine it's still going to be difficult for water to move through. There are some instances where permeability is important. So for instance, we'll often talk about aquifers. Like we mentioned, Oklahoma has 23 aquifers. An aquifer is really just defined as a permeable layer beneath the surface that transports groundwater easily. So an aquifer is this accumulation of water because we've got something here sediment-wise that allows for water to move quickly through the pores and accumulate. This tends to be made of well-sorted and well-rounded sands and gravels. On the other hand, a word you might not have heard is an aquiclude or an aquitard. An aquitard is an impermeable layer, and it prevents groundwater movement. So this is going to be made of some kind of different soil, typically stuff like shales and clay. So we've got a layer, sometimes on both sides of an aquifer, of impermeable surfaces. They're going to keep the water contained within the ground, and that's how groundwater kind of stays in place and forms. Relatedly, we can have different types of aquifers, a confined or an unconfined aquifer. So a confined aquifer is completely filled with water. That would be like this one here, completely filled with water and it's under pressure. They call that hydrostatic head. And typically, confined aquifers are separated from the surface by impermeable layers, or those aquitards. So imagine these confining beds are aquitards. Because they're separated by these layers that are really impermeable, it takes a long time for these to actually recharge. So it takes a long time for water to make it down here to fill them back up if we pump water out. An unconfined aquifer is like this one up here. It has a water table and is only partially filled with water. So there are spaces that aren't filled with water. It tends to be closer to the surface. And because it doesn't have an aquitard above it and it's closer and connected to the surface, it rapidly refills with water. So these impermeable layers can affect how groundwater further down is going to recharge over time. It says the further down we are, the more aquitards we have. It can take centuries for this to refill after you use it, years to refill here, whereas this one might refill very quickly after a rain event because it's connected to the surface in some way. So those were groundwater basics. Let's move on to talking about groundwater movement. This is a really good picture to show you kind of like the zones that groundwater has to pass through as it makes its way down. So starting at the top here, as precipitation happens and water builds up on the soil, water starts to infiltrate the ground. And it begins to seep through the pores of the first sediments at the top, and that's called the zone of aeration. If you think of aeration, it means there's air trapped within here, right? So a small amount of water gets left behind. Some water gets stuck to these particles as it's moving down. But since these pores mostly contain air, water is able to move pretty quickly down further and further. Right about here, we've got something called the capillary fringe. It's basically the boundary between the zone of aeration and the zone of saturation. And this is actually what we call the water table. It's basically where we've got this dry soil up top where water is moving from, and then saturated soil down below. It's called capillary fringe because water can actually move back up into the zone of aeration due to capillary action. You might remember we said based on cohesion and adhesion, water can move up a tube basically. Same thing here, water can actually move back up into the soil from the water table. Eventually, most of the water drains down into the second zone, which is the zone of saturation, and that's just where all the available pore space here is filled with water. So there isn't air like in the zone of aeration. This is what we consider the water table and the aquifer. Everything is filled with water here. We've mentioned groundwater recharge and discharge, so just to kind of define it, recharge is when water is added back to the groundwater supply, and most of recharge happens from rain and also melting snow. So it's basically directly related to the amount of precipitation that we get. And you can imagine recharge time depends again on things like what the soil sediment is made out of and whether you've got an aquitard preventing water from moving further down. Discharge, on the other hand, is similar to how we talk about discharge in streams. It's really just any process that lowers the water table or the amount of water leaving the aquifer overall. That can be normal. It can be that groundwater feeds into a body of surface water, or groundwater feeds into springs, and it can be human-made where we discharge it because we have a well or something pumping it out. So an example here, this is something called a perched water table. But there's an impermeable layer here, like an aquitard, that leaves a little bit of water stuck in this top layer or zone. And so since it can't go further down, it moves across the land and then comes out on the surface. So that's actually what we consider to be a spring. If you've ever thought about where springs come from or how streams first kind of get their beginnings, it's really because of this. Here's another example of a spring. So here's an example of where there's not an aquitard, but here we've got bedrock or something that has fractures in it. And if the fractures are big enough and they meet where the water table is, now water can seep out. So now we've got a stream or a spring coming out there. Just to show you here, here's an example of in the Grand Canyon, natural springs allowing water to come out of the ground and fill up the Grand Canyon. So springs basically form where groundwater intersects with the land surface. Wells are what we do to get groundwater out, and that's essentially just we dig a hole down all the way to the zone of saturation so that we can pump the water out. And again, due to the natural cohesion and adhesion of water, when we dig a hole deep enough into that zone, water is going to seep in and fill the hole, and then we can pump it back out. That's the basics of how any well works. For example, it says, what happens if you dig a hole in the sand on the beach? You probably know if you've ever done this, if you dig close to the water and you dig deep enough, it will fill with water, right? You basically made an empty space for water to move into. So while we have pumping wells that basically do this for us, here's just an example in Kenya of how they get fresh water sometimes. They literally just dig a hole down until it reaches the water table, and then they can scoop it out and carry it in jugs and take it home. So let's talk next about groundwater pH, just briefly. Sometimes it's important to know that groundwater can be acidic. It depends mostly on the sediment that it passes through. So we talked a little bit about this when we talked about water quality earlier this semester, but remember, if we have carbon dioxide or CO2 from the atmosphere or the soil and it gets dissolved in water, it tends to form carbonic acid. So anytime we release hydrogen ions in water, we're actually decreasing the pH, and that makes it more acidic. So the result is that the pH goes down, we've got slightly more acidic water when this happens. So anything with carbon dioxide in it can be a problem. There are natural sediments, though, that can react to this water and change the pH. So for instance, has anybody ever heard that limestone is really good at buffering water? Well, limestone is basically just a common sedimentary rock, but if we look at what it's made of calcite, which is calcium, carbon, oxygen, and 3 of those. Calcite is really easily dissolved in carbonic acid. If you look at this GIF over here, when you put acid on calcite, it immediately starts to dissolve. And what actually happens is that it starts to form calcium bicarbonate. So it takes that acid and forms bicarbonate, which looks like this. And bicarbonate, it's important to know, is a base. So in this case, if you've got things like limestone and they're producing bicarbonate, you're actually changing the pH, you're causing the number to rise, and you're making it more basic. So the acidity of groundwater depends on how much carbon dioxide is making it into the water, how acidic is the rain, and also importantly now, what is the rock, soil, or sediments made out of, and do they produce a reaction that creates a base? You might have heard of this before, but this is what forms karst. Karst is the name for the topography that we have around here. It's also in Kansas a lot, but it's basically where surface landforms kind of develop because this limestone bedrock is dissolving at the surface and underground. And this is where we get things like caves from. You've ever thought about how a cave forms over time? If we look at this picture over here, caves are basically just where groundwater has seeped down through pores or cracks, and it's been able to basically, eat away at soluble materials like limestone. So if we look, at this picture of how a cave forms, it's a little geology, but these holes form in soluble areas in between these impermeable or less soluble areas. So if we've got slightly acidic groundwater seeping in here for hundreds of years, it can eat away these tunnels and things, and that's what makes a cave. It also causes something called a disappearing stream. If you've never seen these before, they're actually really neat. But it's basically, you'll see a stream on the top of the land and then suddenly it disappears down into the ground. And what this is just that there is somewhere along where the stream path is going that is really soluble and the water can eat away at it. So streams that are slightly more acidic are better at doing this, but over time, that water will eat away and can form caves or a waterfall and basically create an opening where that stream just disappears down into the ground. Next big topic for us is kind of what I mentioned earlier, but groundwater exploitation. This is the human effect of using groundwater. Groundwater has really been rapidly exploited, especially just within the last 50 years, with little regard to long-term effects. And the problem is that we need the water to live the lifestyles that we do, but I don't think that we often consider how long it truly takes groundwater to recharge. And so because of this, the way that we use groundwater, there's 4 big factors that are causing groundwater to basically either go away or become polluted. So we'll talk about each of these individually, but the first is simply that we lower the water table by using water, and that creates things called cones of depression. The second, sometimes we contaminate the groundwater with salt. 3, land subsidence means that we cause basically the land to become more compact or collapse. Think of like sinkholes. And 4th is simply groundwater pollution. So first, as we are pulling groundwater out, sometimes we pull out more groundwater than is currently being recharged. And that's what we call an overdraft. So just like at the bank, right, if you were to try to cash a check and it's for more money than you actually have in your account, right, you can overdraft your bank account, you can overdraft a water table too. And so this happens when groundwater is withdrawn faster than it can be recharged. And this normally happens due to overpumping, meaning that we've got lots of wells in the same aquifer and they're all pumping out a large amount, and maybe it's a dry period like a drought. And what ends up happening is that because we're pumping so much water out, the water table itself actually lowers. So basically you start creating a larger zone of aeration and the water table moves further and further down into the ground. And you can see it really moves further down where these wells are directly pumping water out. If we take a look at Oklahoma, this is the High Plains Aquifer, the Olagala Aquifer. These types of situations are more likely to occur in places that are dry, so arid places with little precipitation. They've got warmer climates, and of course, higher populations. So more people needing more water. And if you think about it in this case, if these things are all true for an area, then groundwater isn't really a renewable resource like we think it is. It doesn't renew as fast as these things all need it to. So if we continue to pump it out, it will actually become depleted. So, this big aquifer that we're connected to, studies currently show 2 to 100 times more water in various places is taken out faster than it can recharge. And in some places, this aquifer has already dropped 40 feet further into the ground. So if we continue to pull it out, especially during dry seasons or in urban areas, that's the future of this aquifer. I mentioned earlier it causes something called a cone of depression. So this is just that when you have a well that is attached to that zone of saturation and it's pumping water out and you're overusing it, what can happen is that you basically create a cone of lowering water table right around where this well is. So it means here, because you're sucking water out really strong, it's basically pulling water down at all angles like this. And so in this place where you put your well, as a consequence, the groundwater is actually going to lower or move further down. And if you think about this, it causes problems when you've got lots of wells nearby who are all trying to pump. If they're all causing a triangle or something like this, a cone, you can imagine it's going to get harder and harder for everybody else nearby to also get some of that groundwater. So think of it like drinking a milkshake with a straw. Have you ever had like ice cream or something and you suck really hard on the straw and you can't get any more ice cream out, even though you can see there's ice cream all around the straw, but you've basically created a cone of depression within your cup, right? Well, imagine that on a large scale in the ground. The second big thing that we need to talk about is saltwater intrusion, and that is anytime that fresh water gets contaminated with salt water. So this is more common, obviously, in coastal communities. You can imagine if you live near the ocean that there is going to be some connection, between salty groundwater and fresh groundwater. And what happens is when you put in a well and it's forcing water up and pumping it, it can force that salt water up as well. And that salt water now gets into your fresh water and contaminates it, makes it more salty. Consider that they don't normally mix, right? Salt water is more dense than fresh water, so normally it stays below the groundwater. They've got their own layers, but any kind of strong suction is basically going to force it to move up and diffuse through the fresh water. This can happen in freshwater inland places too. It's more common by the coast, but this can happen around here too. We'll look up pictures of, they call it salt scars. But there are places where you can see on the land that something salty has basically killed all the vegetation there, and it's likely that it's sunk into the ground there and contaminated the water too. Land subsidence was the next one, and this is just when you remove so much groundwater that it causes the sediments to basically become really compacted. So in this example here, we've got some clay and silt, which are those impermeable layers, but then we've got a lot of sand and gravel in that zone of aeration. And as we remove water and we're pumping water out, it's going to cause the sand and gravel to sink further and further, getting more and more compacted, because we're basically pulling out the stuff that was filling all those pore spaces, right? So if you do that over time and it gets more and more compacted, what happens is the land surface itself actually drops down. And so here's where the well originally was placed. Here's where the land currently is. This is actually a major problem, not just because groundwater is declining, but land is too. Here is an example of the city Fresno. In Fresno, there are places where it has dropped almost 43 inches, the ground. It's very common here. It's dropped about 7.8 to 8 inches. The ground itself is declining. So imagine that we keep doing that, right? We're pumping out water and we're causing the ground to become more compacted. What also happens is that sometimes when we're pumping out this water, we create basically pockets of air. And if a pocket of air is left there and the weight of the soil above it gets too heavy, that's how you get a sinkhole, right? So sinkholes are becoming more of an issue, especially around urban areas, because as we're pumping water out, we're creating empty caverns, basically, that are unstable in the ground. So in people's yards, sinkholes are popping up. There was research that recently suggested that about 1,600 of the world's major cities have a 50-50 chance of experiencing subsidence, and more than half of them are located in flood-prone areas. And that means that we expect that major cities are going to continue to move further and further down as the soil gets more compacted. And if they're already in a flood-prone area and we keep moving the ground down, we're going to make floods more likely. And if you think about news, that's already true, right? This picture down here is really shocking to me. They have a post that they've been monitoring USGS for years, and they keep adding dates to it. But the soil used to be here where this line says 1988. And it's taller than the woman is. 2016, look how different it is. Look how far down it's moved because of the water that they're taking out. And you can imagine not only does this suck because now it can flood, but imagine you have structures you're building, like bridges we can see she's standing by. If the soil continues to move further and further down, that poses a problem for engineering. And then lastly, let's talk about groundwater contamination. There are lots of ways in which the groundwater can become contaminated. One is underground storage tanks. So like gas stations, for instance, they have underground storage tanks that store their oil and their diesel that they have to pump and fill periodically. And I used to know somebody at grad school whose job was basically to go to gas stations and check the tanks under the ground to make sure that they weren't accidentally seeping stuff into the ground. It's actually really common. I think she worked for Come and Go. I can't really say in particular, but she said something like there were like 300 tanks in the ground in the state. And of those tanks, most of them were over like 15, 20 years old and had never been checked. So who knows how much stuff was actually leaking out of them. Anytime we have an oil pipeline or underground pipe that's moving something, we've got the chance of a leakage happening. Septic leakage happens. Septic tanks or other things, just like the storage tanks at these gas stations, can also break or wear down over time. And if we don't repair them, now we've got septic fluids moving down into the groundwater. Landfills are notorious for causing groundwater problems. This is depending on the way they make the landfill. Older landfills, if you didn't know, are what we call an unlined landfill, meaning we really just dug a big hole in the ground and we threw trash in. So obviously every time it rains, seepage off that trash is going to move into the ground. We also bury waste, so that becomes part of this layer that can hold up water and or seep further down into the ground. Nowadays, I think they require that landfills line it, and lining it means you literally put in a layer of some kind of lining or some basically impervious surface. That means at some point when it fills in, it's not going to be able to seep any further into the ground. In places around here where there's a lot of agriculture, pesticide and fertilizer infiltration is a real thing. So it's kind of related to the second one down here, but irrigation and agricultural practices heavily influence the water. If you don't have things to basically catch the pesticides and fertilizers as it's running off, it's going to seep into the soil and contaminate the groundwater. We talked about this one earlier this semester, but mining activities. Remember that mining activities can release things into water that changes the acidity, changes the color of the water, obviously can increase things like heavy metals. One we don't think about a lot is de-icing. We put salt on roads all the time whenever it ices or gets cold, right? And then if you think about it, when that snow melts, now it's got all that salt in it too. That snow becomes water, now it's salty water, and now it runs off into rivers and streams and percolates down into the ground. And of course, if we have any major type of contamination in our surface water, it will seep into the ground, into our groundwater. And so I show you this picture over here on the right to say that all of these things can contaminate groundwater, and then when you pump it in a well, you're getting all of that contamination. So we have to monitor these things very, very carefully. or we have to treat it. You might have heard that sometimes groundwater has to be treated. It means that it literally comes out in a condition we can't use, and we have to basically clean it and purify it first before we can use it. So I have a video here. I think it's about 10 minutes. I'd like you to watch if you're at home, because we're going to watch it in class. But this is just a professor who talks about groundwater contamination and shows you some pictures about like how it's happening.